My name is Alin Drimus, and I come from University of Southern Denmark, and I will allow me to present a paper called Novel High-Resolution Tactile Robotic Fingertips. Well, I will start with an introduction and a motivation. Why do we build such fingertips? And then I'll show you how we start to develop such a fingertip by starting with a single tactile cell and how do we characterize it. We also have a rough mathematical model for how it works. And then I'll show you how we go to an array sensor and also some things about the fabrication and the electronics. Then I'll have some experimental results and I will just briefly conclude with an overview. So our motivation in robotics is that we need tactile sensors for many things, but mostly we need it for manipulation. For example, we're interested in grasp force control, contact locations, or kinematics. We're also interested in assessing the stability. Furthermore, we might be also interested in unknown objects. For example, you want to know different features of these objects. So you will use tactile sensors for exploration. We also are interested, for example, in detecting different contacts to external agents. Well, in our case, the motivation is Hector. This hexapod robot, it's a bio-inspired robot, and it was part of the EMICAB consortium, which was a FP7 project. And we were partners there, and our task was to build tactile sensors for Hector. These tactile sensors would allow Hector to better inspect or to find out things about the environment. So this robot should be autonomous and should walk in different terrains. So we had to design some tactile sensors that would give a lot of information about the environment. And what do we want actually from an ideal tactile sensor for this application? We're interested in pressure distribution on the fingertip. And we're also interested in detecting information like slip or vibration, what happens in the ground. We're also interested in using simple sensors. And of course, because the fingertip will have a curved surface, we're also interested in having some sort of compliant or possibility of having various shapes. We're also interested in having an increased sensitivity and, of course, a high spatial resolution. Well, because this is a robot and will walk quite a lot, it has to have a robust sensor because it might get easily damaged and it has to be easy to replace. And if we find some interesting surfaces, we want to know if they are slippery, soft, and we also want to estimate, for example, different contact conditions, like find out the pressure, find the angle, and the force. And of course, the electronics should be simple. Well, after a comprehensive survey over possibilities for building tactile sensors, we have decided on piezoresistive rubbers to build such a sensor. And they're basically based on a non-conductive elastomer, which is a rubber, which has electric conductive particles inside, which are dispersed. And when you have two electrodes on the top side and bottom side, and when you apply a force over these electrodes, these particles, the distance between them, it's decreased. And then due to this distance decreased and percolation theory, you get a drop in resistance. And this is how the rubber looks like. And here you have the curve, the FR characteristic, force to resistance. And you might see here that we have a hysteresis, and we also see that we have quite a smooth curve for this. We're not really that interested in the hysteresis because this is an elastomeric-based material, so we're going to have that. And we're not also interested in exactly the force measurement. So we're also interested in just having a rough estimate of the force. Well, so in order to characterize it, we built one single cell by just having one electrode on the top and one on the bottom. And this is how the curve looks like for 20 actuations, pressing and depressing. We have also tried thousands of actuations. For example, this is 13,000 trials, and we have a repeatable output. You can see here that the curves overlap quite nicely. This is not really that good for static loads. If we look here at how the output varies in a static scenario for 2 minutes, we can see that the output varies for about 10%. So this is mostly good for somehow dynamic environments. And we can also see that there, for very small forces, we can see this output is not really that nice. So this is basically due to the contact resistance. Well, we have then built a model. How do we actually model the output of the cell? This is a big mystery. So we have tried to find some sort of an approximation of how this tactile cell works. And we use a model based on general effective media, where the conductivity of the material somehow around the percolation threshold follows power laws. Then we have also added the stress, and then we have figured out some curve fitting parameters, and we have this blue line is the simulated model. And this is the measured characteristic. And you see here, on the very low forces, we have a problem. The model doesn't really follow the experimental results. And this is basically because we cannot model that well the contact resistance. So we actually want to have this model, we will have this model matching closer when you have a higher force. Well, how do we do data acquisition? Compared to the previous paper that you just saw, we have a different approach. We have an array of electrodes on the top and an array of electrodes on the bottom, and we do multiplexing really fast, and we address these columns and these rows only one column at a time and one row at a time. And just by doing this, we measured the resistance at their overlapping point. So if we do really fast for all the columns and all the rows, we get resistance measurements in all these overlapping points. And this is how we can build arrays. What is a measuring principle is just a voltage divider. So we can do this really fast, we can get a tactile image. Well, we want to actually develop a fingertip array. So this is the target we have in mind. It has 60 cells, and it's arranged in 12 columns and 5 rings. How do we build this? Well, the fabrication is labor intensive, I would say. We start with a 3D printed base. We have some copper rings, and then we deposit some silver epoxy rings on top of those. And then we have the piezoresistive rubber cut in a flower-like shape, which we cover with a flex PCB layer. And then at the end, we just have a protective nitrile layer. And this is how we get a fingertip. These are the steps, the fabrication steps. This is the first step with the epoxy and the rings. This is where we apply the rubber. Then we apply the flex PCB and the outer protective layer. And these are the final prototypes. You can see they have also some small designed electronics as well, together coupled, and this is just for increased robustness. This is just some textile impregnated with some polymer. Well, what about the electronics? They're miniaturized, and they do the signal conditioning, the multiplexing, and pre-processing of the data, and of course they also transmit the data to the robotic insect's brain. And they are quite small, and they're fitted in the robotic legs. Well, we tested the sensor, and you might be curious, how does the sensor work? And this is the tactile images that we get in real time from the sensor. You see, I'm just touching the sensor in different points, and we get the images that look like this. Well, these are some experimental results. We have different orientation of our fingertip, and we get different tactile images. You can see whiter is for a higher force. And this is basically a measure of the pressure. We then went a little bit further, and we wanted to learn the force and the angles of thousands of images. So we have done 8,000 of images in different angles and forces, and we have collected all the tactile data. And we try to use this tactile data to generate a model. If we use just the tactile data, can we estimate the force and the angle of contact? And the answer was yes, we have done this, and we have based the mathematical model of each cell, and of course we have used also the area of each cell. And when we added all this together, we have obtained the estimated force from our model and the measured force. And you can see that the curve is very nice matching. It's like an identity curve. The only problem is for very low forces, we have a small problem, and this is because our mathematical model cannot account for the contact resistance. But however, this curve is good enough for our purpose. And our purpose is to figure out the force when the robotic insect is walking. And we use this tactile sensor to give tactile data corresponding to pressure. We have 500 frames per second, and we have 60 cells. So we have quite a lot of data coming to the insect's brain. But we also give shorter data like force estimate based on this model. We also give angle estimate, the center of contact, and we also give other things like number of cells touching the surface or average value. So the application of this sensor is this hexapod robot that I said some things about, and now you can see it in action. It has the sensors on the front two legs. I hope this works. Yes. This is a biology-inspired model robot, and it has different walking models, biology-inspired from the stick insect. However, in this case, the sensors that we have, they're really good for going over rough terrains, and there's no problem if we have a very, let's say, high forces applied. So we can have overloads of 300, 400, 500% of force to this tactile sensor. So it doesn't get damaged so easily. All right. So I've shown you a curved fingertip with high spatial resolution. I'm talking high spatial resolution in comparing this to the sense of touch in humans. And this is similar in terms of spatial resolution. And this is based on piezoresistive rubbers. The generated tactile data is for 60 cells, and we have about 500 frames per second. Of course, it has a very increased robustness, and we have a possibility to extract the contact force and angle information in real time. And of course, the most important thing is very cheap to manufacture. Thank you. If you have some questions.